Okay, so first of all, good evening for you who are based in the UK. And let me thank the organizer for making this very nice workshop possible. It's really a pleasure and an honor to be speaking here with you. And I really thank them for inviting me to give my presentation. So as you can see from the title, the topic of my presentation is objectivity, and specifically objectivity not in the standard the quantum mechanical framework, but rather in a more generalized version in a framework called general probabilistic theories, which allow us to address all possible types of physical theories. Okay, so let me start by thanking my co-authors, Roberto Salazar, Jarek Korbic, whom I think spoke today, and Pavel Horodecki. So we decided to study objectivity from a slightly different angle than what is usually done. So why do we do so? Well, we know that classical theory is objective. What does it mean? It means that essentially we have different observers that observe something and they agree on what they see. On the other hand, in quantum mechanics, this is much harder because since the measurement is disturbing, so it's much harder to talk about some sort of objective reality that maybe somehow pre-exists the measurement, right? Because we know that we can only talk about what happens after a measurement in terms of what we can describe. This goes back to what also Bohr claimed, right? I mean, this is exemplified in this nice cartoon here that, again, yeah, you are the one, but who knows? Because, you know, in the quantum world, strange things happen. So the question is, how do we reconcile the classical perspective on what's going on in the world, which is objective, with the underlying quantum theory, which doesn't seem to be let's say, stable in terms of objectivity. I mean, the objectivity in the quantum world seems more fragile. So the question is, how can we explain then the way classical behavior and objectivity arise out of the quantum world? So they have, in the past, people have put forward different proposals in this respect. The first was decoherence, which was then upgraded to quantum Darwinism, where we have the survival of the fittest states, which also happens in the coherent fittest state, in this case means a classical state, and also in the quantum Darwinism, the multiplication of them, right? Because information is redundantly stored. And finally, Jarek Korbic and Pavel Horodecki and Richard Horodecki proposed a new approach, which is called SBS, Spectrum Broadcast Structure States. And this is essentially the approach we focus on in this presentation. So the big question we want to understand is, what part of quantum theory is responsible for the emergence of classicality? So we are motivated by a very foundational question. And in order to answer that question, instead of working within the framework of quantum theory, we go beyond. So in other words, we want to look at quantum theory from the outside as a sort of a privileged island in a landscape of possible different theories, right? And in this way, we are able to get also a new perspective of alternative theories to quantum mechanics, which will become maybe significant in the future when we try to extend it to new physical regimes. So this approach of going beyond quantum theory allows us first to answer this question and understand essentially how quantum mechanics ensures the emergence of objectivity, and also we understand how this works in alternative theories, right? So what does it mean to look from the outside? So instead of focusing on the quantum mechanical formalism, we upgrade the formalism to describe any possible physical theory that is conceivable, that admits probabilistic processes. And then we want to see which aspects I need to impose, which conditions I need to impose on these generalized theories in order to, let's say, retrieve the same results as in quantum theory. And this is what we answer. So before we get into the new results, I need to explain the framework in which we conducted our analysis. And this is the framework of generalized probabilistic theory, as it's called, specifically a version that utilizes diagrams. So what happens in this case? So we recognize that the basic element that we have in any possible physical lab, because remember that physics should give experimental, should give predictions to experimental results. So we need to describe what an experiment looks like. So an experiment is essentially, think of a quantum measurement, a collection of processes that can occur in a given circumstance. And there is also a classical outcome associated with that. And the classical outcome is, in this case, labeled by the subscript I here. So we have a collection, we represent it as a box with an input wire and an output wire. So you should read this diagram from the left to the right. So A is the input system, so it's written on top of the corresponding wire, and B is the output system. So again, what happens in this case, a test essentially is an experiment where there is a system A that comes in, something happens, a classical outcome is generated, and then we have system B coming out of that device. So essentially also the shape of this diagram reflects the idea that this test is represented by a device that you can connect in a larger circuit. So just to fix some terminology, whenever we have a deterministic test, so in other words, we don't have a classical outcome because we can always predict what happens. Whenever we know the input, we also know what the output is. We have what is called a channel. So in that case, there is no classical outcome. There is only one element in this collection. So channel, this mirrors the same definition we have in quantum theory. It's actually useful to consider other types of channels and tests where there is no input and correspondingly no output in the dual situation. In particular, if we have no input, as you can see from the diagram here, there is nothing on the left. So we can think of this as initializing system A on the state row. So in other words, this row represents a preparation process. Dually, so some tests, for example, when we have a destructive measurement, a demolition measurement, there is no output system coming out of it. There is only the classical outcome that is essentially what I can see out of that experiment. But there is no there is no output of that. So in this case, what we have, what we call a measurement. So we have no output here, and the objects that make up the measurement are called effects, in a similar way as the elements in a POVM are sometimes called effects too. Okay, so what can we do with these elements that are generated, let's say, that are considered in this setting here? So we can build circuits. Like having a diagrammatic language means that we can combine all these pieces together and build like a larger circuit. So let's see what happens in this case, just to help you understand what's going on here. So we have a state rho I, okay, that's prepared for the bipartite system AB, A Alice and B Bob. Then Alice performs a test on her system, Bob performs a test on his system independently, and they get outcome J and M respectively. Then Alice does something else while Bob does nothing. So Alice applies a new test, AK prime. And finally, after that, they both measure their respective system locally. So they get outcome L and N in this case. So what is this? So in this scenario, essentially, we started from the preparation of a state and we ended up with its destruction through a measurement. So what do we get out of that? We get a probability. So whenever you see a diagram when such that there are no external wires, like in this one, because if you look at the very left and the very right, you don't see any wires. So again, this is something with no external wire, and it represents the joint probability of all these events occurring in the circuit in this specific realization. And it's also an instruction on what we need to do in order to do the experiment, because we just need to connect all the devices associated with these various elements. So you see, it's a very intuitive representation, but very powerful, because you see, I'm not making any assumption. You don't see Hilbert spaces, you don't see anything. So this works in any possible physical situation. Now, if we want to say something more, and we want to make more predictions, we essentially need to basically develop some more mathematical framework based on this abstract language of diagrams and circuits. And this is done thanks to the probabilities we introduced, because the probabilistic structure essentially allows us to consider some vector spaces that are real. Okay, we'll have a vector space of states, which is real. Think of that, because in quantum mechanics, also the vector space of density matrices is real. And dually, we have a vector space for the effects, and they are both ordered. So what I mean is order, there is a cone there. For example, in quantum mechanics, we have the cone of positive semi-definite matrices. Okay. So this structure, linear structure, allows us, of course, to define sums and then convex combination of states. And here, and therefore, we can talk about when something is pure or not. So the key concept to understand purity is coarse graining. So I want to make a classical example of what I mean by this. So we have when we roll a die, we have some atomic events, because they cannot be further decomposed, like the outcome is 1 or 3 or something. But we have some others that instead are coarse graining of atomic events. And in this case, we have, for example, the outcome is odd, which is the coarse graining of the events associated with the events associated with 1, 3, and 5. And this notion of coarse graining allows us to define what a pure state or pure transformation is. So we say that something is pure if it cannot be written as a non-trivial sum. So in a non-trivial coarse graining of other transformations. So in other words, there is no way that a pure state arises as a convex combination or something like that, or sums of other states. So it cannot be further decomposed. This really captures the essence of mixedness. And finally, a very crucial axiom in this respect is something we call causality. So what happens is that in causal theories, they're called causal because information cannot loop back from the future. So what does it mean? If I do something now, what I do now doesn't depend on what I will be doing next. So the outcomes of future experiment don't influence the choice of tests performed now, okay? And so this can be seen as a no signaling in time, but this also implies no signaling in space. Since essentially causality forces information to fly from to move from the past to the future, we can do a sort of condition. We can condition a future test on the result of a past test, because information goes from the past to the future. And in this way, we have what we call, for example, the measure and prepare tests. So what are those? So essentially, first I apply the measurement AI, and if the outcome is I prepare a state rho I, which is normalized. What does it mean normalized? It means that essentially, if I apply a measurement to it and I coarse grain over it, I always get 1 as the probability I get. So that's what it is. Okay, so this is really important. And causality also allows us to discard systems. So the causality is the thing that in quantum mechanics allows us to discard systems with a partial trace. So that's really the property. So of course it's satisfied by quantum mechanics. So now that we understand the theoretical framework, we're going to talk about the rest. The rest is essentially what the new work we did on decoherence and objectivity. And if I had time, I'm going also to talk a little bit of locality in classical theory. That sounds a little bit strange because we are used to think of locality let's say the issue of locality in quantum systems, but there is something to it as well. But again, if I have time, I prefer to stick to decoherence and objectivity, which are really the core of our results. Okay, so let's start from decoherence and all the associated. So the first step is to understand what classical theory is from the point of view of generalized theories. So in particular, in this framework, we focus on finite dimensional systems. So again, we want to focus on finite classical theory. So we have probability distributions over a finite set. And these are the states. The state space is a simplex. And we know that the extreme points of this simplex, so here you have some examples, so the vertices are the pure states and the rest instead are mixed states. The important thing is that the pure states are jointly perfectly distinguishable. What does it mean? It means that there is a measurement that if I don't know which pure state I have in the system, I can make a measurement and this measurement will tell me the state with certainty. So that's what it means. This is what it means. They are perfectly distinguishable. And another important thing is that the cone of effects is the dual cone of the cone of states. For those of you who know a little bit of cones, and I'll tell you more about this shortly. Let's say. Okay. If we want to talk about decoherence, we definitely need to identify a classical subtheory of a given theory, because definitely when I have decoherence, I go to a classical subtheory. Notice that classical systems are already present implicitly in every description of physical theory through the classical outcomes. But now we want also to talk about them in a more explicit way. So they say we want to understand the classical outcomes as emergent from a classical limit present in the theory and an associated decoherence process. So what do we do in this case? Remember that pure states are, in a classical theory, are perfectly distinguishable. So what we do is that we look for sets of perfectly distinguishable pure states, and we want to pick the largest set of states such that it contains all the pure states are perfectly distinguishable. The question is, can we find such sets, maximal sets of perfectly distinguishable pure states? The answer is no. And we have a counterexample. So curiously, to have this counterexample, we need to start from classical theory, in practice from a classical treat, a three-dimensional system. So this is the state space of a classical treat. If we take a section of the cone of effects, we would have the same picture as we have for the states. So here, instead of allowing all the effects that you see in the orange triangle, we put a restriction, we set a restriction, and we only pick the effects that are in the blue triangle. So we take a much smaller cone. What happens in that case is that if we reduce the number of effects, what can happen is that we lose tomographic power. So sometimes some states become indistinguishable, but this is not the case. So we still have a classical treat from the point of view of the state space. However, the pure states alpha 1, alpha 2, alpha 3 are no longer perfectly distinguishable, and there is no way to make them perfectly distinguishable, not even if we take composite systems of this. So there is this theory here, which is very strange, if you wish, doesn't allow for a classical limit, even if we take a lot of copies of this system here. This is the elementary system with which we construct the whole theory. Okay, so we want essentially to rule out these pathological cases. So let's assume that such states, maximal sets of perfectly distinguishable states exist. So a classical theory, what is that? It's simply a classical, is the convex hull of this set of pure states. And basically, this is what I wrote here. And what are the effects? Because remember, in a theory, we need to talk about states, but also about effects. Because we saw in the previous example that just talking about states is not enough. Because if the effect space is particularly bad or has strange restriction, then the theory doesn't behave in a classical way. So then what we do, imagine that we have this classical subtheory alpha as subtheory of the original theory. And then what we do to understand what the effects are, we restrict the effects of the original theory to that subtheory. Of course, some effects will become indistinguishable because they will give the same probability on all possible classical states gamma. So if that's the case, we say that two effects are equivalent. So we introduce an equivalence relation in more formal terms, and we construct the quotient set, which is the set of equivalence classes of effects. Well, it turns out that this construction is well posed because the resulting set of effects is nothing but, again, a simplex. Okay? Well, it's not exactly a simplex. It's I mean, it can be understood as a section, I should say, is a simplex. I'm sorry, I wasn't very precise here. And it's generated by the effects that distinguish those pure states. Good. So once we have classical subtheories, let's see what we need for a given process to be a decoherence. So we want a process to be a decoherence that maps all states of a theory to classical states. I'm talking about full decoherence, like completely dephasing map in the quantum case. Here, we just call it decoherence. Another thing is that we want to look for a channel, because when we reach the classical limit, this isn't a probabilistic process, it's deterministic, because classical theory is stable. So we want to look for a channel specifically. And this channel, of course, if something is already classical, it should stay classical. So everything, so we need to look for a channel. This channel should map all states to classical states, and classical states should be left invariant. So this is the definition we give then of complete decoherence. Again, it leaves classical states invariant, and it maps every state to a classical state. So you see very minimal requirements for a decoherence. So what are the properties that follow from this definition? That if we apply the decoherence twice on a given row, it's like applying it once. And notice that actually this doesn't mean that applying that, essentially taking the square of this channel is actually equal to the channel itself. In order to have that, we need to assume another axiom, which is called local tomography, which are not so willing to assume. Anyway, for those who know, again, general probabilistic theories. Otherwise, just think of this. So essentially, we have a sort of slightly weaker version that this thing, when we apply it twice, it's like applying once. But this happens for every state, not just without states. And then it happens what we expect. So the set of decoherent effects coincides with the set of effects we defined through equivalence classes. Okay, so with restricted effect, we took equivalence classes. This is the same set, can also be generated by taking the original effects of the theory and then decohering them. However, there is something quite strange going on here. We know that a classical pure state is left invariant by the decoherence, by definition of decoherence. However, the effects that distinguish those pure states, which are again classical effects, right, in general are not left invariant. So we have an asymmetric behavior between what happens on classical states, which are left invariant, and what happens on classical effects, which are in general not left invariant, but they are just transformed to something equivalent. So there is a little bit of an asymmetry here in general. So this is as far as a definition goes, but again, a definition is not so interesting if we don't have examples of these things we are introducing. And the main question is, do we have at least one decoherence in every causal theory with classical subtheories? The answer is yes. So in order to do that, we need to consider the measure and prepare test on the classical set. So we measure with the effects that distinguish those classical pure states, and then we prepare the corresponding classical state. This is possible because we have causality. So causality is really what matters here. Now, if we take the full coarse graining of this test, so essentially we have a test, but we don't know the outcome, so we sum over all possible outcomes. What we obtain here, this d hat here, is a channel which we call test-induced decoherence, because it's a complete decoherence to the classical set alpha. So for every classical set, we have a complete decoherence. In particular, this type of decoherence, which we call the test-induced decoherence, has stronger properties. The square of it is equal to itself, and not only that, also the classical effects are left invariant, not just the classical state. So it's more symmetric. So this decoherence is always guaranteed to exist and has very nice properties. When we talk about existence, then we should worry about uniqueness. Is the decoherence unique on a given set? The answer is, unfortunately, the situation here can be very, very varied, very strange, and so on. Even within the same theory, we can have different classical sets that have, in some cases, a unique decoherence, in some other cases, multiple decoherences. This is an example. This is the state space, is a square. So instead of having the block ball, we have a square here. And the classical set is alpha 1, alpha 2, that segment on the vertical side. The decoherence is here represented with an arrow here. And we see that in this case, we can prove that this is the only decoherence that exists, that maps rho, that projects it to that state here. On the other hand, if we pick the classical set associated with a diagonal, alpha 1, alpha 3, then here we find that there is a continuous family of complete decoherences, which is parametrized by a continuous parameter t. And here you see two examples. So you go from the vertical one or to the horizontal one to something in between, according to the value t takes. But in these theories, decoherence can be even more surprising, because we normally think that decoherence should decrease purity and make something more mixed if we start from a mixed state. And this was indeed one of the additional requirements that was imposed in two works by Richens et al. And Lee and Selby. They require the decoherence to be purity no increasing on top of the requirements we imposed. So in other words, mixed states cannot become pure. And the question is our definition more general? So is it true that in some theories we have purity increasing decoherences? The answer is yes, again. And again, the counterexample is given by the square. So here, notice that we have the state rho here on the side, on the upper side of the square. Again, the classical set is the vertical side, alpha 1, alpha 2, that segment. Decoherence, we see, moves rho to the projects rho to that segment. Rho is mixed in this case because it's a convex combination of alpha 1 and alpha 4. It's not an extreme set, an extreme point of this set. And therefore it's mixed, yet it's decohered to alpha 1, which is pure. So in this case, decoherence increases purity, which is very different from what happens in quantum theory. And we showed in that paper, this is associated with state spaces where we have this sort of sides of the state space that are parallel essentially to the direction in which the decoherence occurs, like in this case of the square. Okay, so this is as far as decoherence is concerned. Now let's talk about objectivity. So what is objectivity? So we had first an informal definition in Olivier and all paper. So we say that a state is objective if many observers can determine it without disturbance and agree on their findings. So there was this initial theorem by Horodetzky, and Korbich, where they show that if we make a suitable sense of this objectivity definition, we can show that objective quantum states are all of this form here, so which are called SBS states. So what they are convex combination. So there you see there are separable states. There are where we have on a system S, we have an orthonormal basis, and on each of then we have n systems E sub n, and for each of those states here have orthogonal support. Okay, so what can we say? Can we try to reproduce something similar in general theories? So in order to do that, we go to a similar setting to the original proof, so which is the setting of quantum Darwinism. We have a target system, several environments, one for each observer, okay? And there is an observer that acts on a referee S, as a referee on the system S, and this observer measures along some classical set alpha. Sorry. And we have the other players around that win if they're able to determine the state of S without disturbing the overall system that are shared. So essentially, we want to explore the correlations and so on in order to find which state S is. So what do we mean by non-disturbing? We say that a test is non-disturbing.
I just let you know you've got 5 minutes.
Yes. Non-disturbing if the summation over AI on that row, on that state row, gives the state row. Okay. So in this case, we focus on a class of tests which are called sharply repeatable tests. So it's a test where essentially if we apply Pi and Pj, we then just get delta Ij and Pi. So somehow similar to von Neumann measurement, but there is more, because in quantum theory, on top of von Neumann measurement, we also have quantum instruments where we have essentially projectors on some orthogonal subspace, and then we prepare states that are supported on that orthogonal subspaces. Okay, the important thing is that we can construct those sharply repeatable tests in every causal theory, because as long as we have perfectly distinguishable states, if we do a measure and prepare, where we measure on the perfectly distinguished measurement and we prepare those states rho I, we get a sharply repeatable test. So they exist in all causal theories. And again, we add a condition that was originally introduced in the original quantum paper, which is strong independence. So the players cannot cooperate. The only correlation between them is the common information about the system. Again, so just only with causality, we are able to recover the full result of the SBS form. So in other words, all objective states are of the SBS form in all causal theories that admit perfectly distinguishable states. Of course, this is slightly adapted because we don't have orthogonal states in non-quantum theories. We just have perfectly distinguishable ones, but essentially everything works. And on top of that, this proof is more general, also because even if you want to apply it in the quantum case, because it also works for measurements that are not von Neumann, they're not projective. So same result as in quantum theory. Notice the wild landscape of decoherence. Sometimes they are unique, sometimes they are not, sometimes they are purity increasing, yet for objectivity, we have a unified result, the same result as in quantum theory. So maybe, yeah, I can briefly, I can skip this. So essentially, this is about when we have different classical systems.
You are okay for time. You've got 3 minutes before questions begin. So you've got like 8 minutes total.
Oh, okay.
So you're fine.
Okay, then maybe I can just say very, very briefly what's going on. Okay. So what happens when we have, let me go. When we have different systems and we have classical system on each of them. So can we construct a classical system for a bipartite system starting from classical system on the components? So to do that, what we do, we consider the so-called minimal tensor product of these two sets. So in other words, we take all convex combinations of tensor products of states in alpha and states in beta. Okay, so this is what we do here. But is that possible? Can we construct that thing? This is actually not so trivial, because the product of two pure states may not be pure. There is a counterexample in quaternionic quantum theory. And on top of that, if we have non-maximals, if we have maximal sets, when we take the product of those, we may still get a non-maximal set, which is problematic because we require this to be maximal. And again, we have a counterexample for that. So in order to rule out this sort of problem here, we need to talk about we need to impose two axioms. One is that the product of pure states is pure, and the other one is the information locality introduced by Hardy, whereby the product of two pure maximal sets is still a pure maximal set. And these are associated with some sort of locality in the emergence of classicality. If they fail, there is some holism in the way classical systems are constructed. And if anybody is interested, I'm going to talk about it later after I'm done. So let me go to the conclusions. So what did we learn? Not all physical theories allow classical subtheories. For the theories that allow that, and for each classical subtheory, there exists a decoherence process, which is induced by a test. So again, like in quantum theory, we measure, we coarse grain, and we get a decoherence. And the different thing is that the behavior can be extremely different from the quantum one. We can have non-unique decoherence, continuous family even, and even purity increasing, so very unusual way of decohering systems. Yet, despite this variety of behaviors, objectivity is universal. Objective states exist and are of the same form in all fundamental theories. And with that, I'll leave you with some references. So I think this is a result that deserves further study to understand what else regarding the emergence of classicality is universal in physics. So thank you very much for your attention.
Thanks so much for that talk. That was really enjoyed that. Okay, if anyone has a question, please raise your hand. Maybe I'll just ask you to clarify something. Yes. So you had this equivalence at various points between the theory being causal and having various other properties, but I think I missed the notion of causality as it existed in this framework. So, yeah. I mean, I know what we mean by causality more generally, but could you just expand a little bit on what we mean by causal here, and in particular, why it would be that those theories which are causal are the ones which have classical subtheories which we can decohere to?
Okay, sure. So causality, here I gave just an informal definition that essentially the probability that a transformation occurs is independent of the choice of tests performed on its output. So let's get slightly more mathematical here. So imagine that we have a preparation of a system. This preparation can be deterministic or not. For example, I can prepare something in a probabilistic way or not, or deterministically. And then what happens is that I apply a measurement to that. So we can, let's say, understand causality as a sort of no signaling from the future. So right now, if I look at the joint probability of preparing the state rho I and measuring with the measurement bk, let's say, if I coarse grain over the outcome k, because this is the future, so it's like whenever we do no signaling, we always sum over the things we don't know, right? As we do no signaling in space, it's when we essentially analysis side, we sum over Bob's outcomes of measurements. In this case, we sum over the outcomes of the measurement over the possible effects. So this sum, so this joint probability of preparing that and measuring using measurement, let's say AK, sorry, if we sum over the outcome K, this is independent of the choice of the measurement. So if I have measurement BK instead of AK, I still have the same. So roughly speaking, this can also be understood as the fact that, for example, all measurements sum to the same thing, okay? And this thing is precisely what we use in order to discard systems. So this is true in quantum theory because all POVMs sum to the identity. If you go to theories like let's say what they are called process POVMs, which are POVMs that are applied on quantum channels rather than quantum states, that property is no longer true. In that case, in that theory, causality fails. Now, the reason why decoherence exists in that situation is that essentially causality tells me that preparation always occurs before a measurement. So whenever I write down something in a circuit, as I did here, right, what I write in the left causally precedes what I write on the right. So if I do something, if I do row I can choose a j, let's say, based on the outcome I. So because that information on the outcome I travels forward in time. And that essentially is the reason why we can talk about these measure and prepare tests. And so first I measure with AI, then if I obtain outcome I can condition my following preparation of the system based on this outcome I. And this was crucial in the definition of decoherence, because the test induced decoherence here, there we go, no, here, right, is constructed starting from a measure and prepare test, which we know it exists if we are dealing with a causal theory. If it's not causal, we don't know what to say.
Okay, this makes a lot of sense. Okay, thank you. So essentially, we can boil it down in a sense to the definition of causality, which we've used here, lends us to having deterministic outcomes, or like outcomes which we can which have a classical nature, which we can use to then prepare things deterministically.
Exactly,
So
precisely.
Kind of
yes, exactly.
Okay.
So we can use those classical outcomes to prepare something else, or to do something else. Yes, which occurs afterwards. Yes.
Okay. Thanks so much for this talk. I think we're right on time to move on to the next talk.